Good afternoon to one and all. I am Mauni
Yeah,
Patandi, a research scholar in the Department of Mathematics, NIT Jamshedpur. I am glad to introduce our renowned speaker, Professor Dr. Ali JabAllah. Sir achieved his PhD degree in mathematics from the University of Münster, West Germany, in field of algebra and algebraic geometry. He is a professor in Department of Mathematics, College of Sciences, the University of Sharjah, UAE. His research interests includes commutative algebra, fuzzy sets, algebraic geometry, and ordered sets. Also, he has published more than 30 research papers in highly recognized journals. He has supervised several PhD and MSc theses for universities of different countries like in Oman, India, South Africa, and Tunisia. Also, he has been visiting professor in Waikato University and University of Münster, Germany. He has been granted for several research projects. He was honorary research fellow at the Department of Mathematics, Auckland University, New Zealand. He has been nominated in Who's Who in the World 12th edition 1994. Now I would like to request Professor Ali Jawallah sir to deliver his lecture on overrings of integrally closed strings. Handing over to you, sir.
yeah. First, I would like to thank the organizer for giving me this opportunity, especially Dr. Ratnesh Kumar Mishra. Thank you very much. It's a great pleasure to be in this great conference, and I'm also benefiting from attending many of the wonderful talks. Now, my talk today is about overrings of integrally closed rings and related ring extensions. This is mainly about some finiteness conditions on the set of intermediate rings and some ring extensions. We start with the ring extension of integral domains, and we define the set of intermediate rings. These are rings T containing R and containing S, and of course with respect to the same operations. And we consider the conditions that is found in the literature with FO, FE, FIP. And this means the set of intermediate rings is finite. Okay. Another related condition is FC or FCP. It means that each chain of distinct intermediate rings from R, from this set of intermediate rings RS, from the interval of rings RS is finite. Okay. Now, if S is the quotient field of R, then intermediate rings, they are usually in this extension, they are usually called overrings of R. And R is called FO domain if the set of overrings is finite, and R is called FC domain if each chain of overrings of R is finite. Now, we need another definition. We say that the ring extension is of finite length if there is a non-negative integer L such that every chain of intermediate rings is of length K here that is less than or equal to L. And the smallest L with this property is called the length of the chain. Basically, the length is the length of the largest chain in this set of this interval of intermediate rings. Now, the main problems that have been dealt with in the last 2 decades here determine condition under which the ring extension RS has FIP, that means has finitely many intermediate rings, or also determine conditions under which this extension has FCP, that means has only finite chains of intermediate rings. Another problem is to compute the cardinality in the length of the interval of ring or RS. Now today I'm going to focus on the second problem because of time. The first problem can be found in many recent paper. Okay. Now after this introduction for the finiteness condition, finiteness problems, first we focus on FO integrally closed domains. We find the length of chain in normal pairs. Now, in normal pair, we define what is a normal pair, just in 1 minute here. And we find also the number of intermediate rings in normal pairs. And then non-integrally closed Fieb extensions of integral domain. Also, we give the related result about the number of intermediate rings. And in the case of integral extensions, that is still, there is no satisfactory result about it. We consider an example and we give results related to that example. Okay. Now let us start with FO, integrally closed domain. Again, let RS be an extension of integral domain. We consider R star the set in S, small s in S, that satisfy a monic polynomial Px in Rx. They are called the integral element. So R star is the set of all integral elements. Now, if R star is equal to R, that means that there are no integral element other than the element of R, then we say that R is integrally closed in S. And if every intermediate ring T and the interval of ring Rs is integrally closed in S, then RS is called normal pair. Normal pair. Okay. In the case where we are dealing with the Fieb extension, that means the number of intermediate rings is finite, and R is integrally closed, then we can directly conclude that we have a normal pair. We don't need to check integral closure for every intermediate rings because of the finiteness condition here. Always when we have finiteness, we have stronger result. Now, the first result concerning the number of intermediate rings and the length of chain of intermediate rings appeared in 1997 in Mathematische Zeitschrift. The result says in modern terms, if R is in FO integrally closed domain, that means in integral domain, integrally closed with the finite number of overrings, then the number of overrings can be approximated with this product over the maximal ideals of R, 1 plus the height. Now the height is the length of a chain that finishes in M, the height of M. Okay, I will explain with an example what is the height. Okay, and this is for the number of of overrings. Now there is a related result where we have RS, not RQ of R. It is very similar. So I'm stating this to give an idea of what is going on. Now, number two, about the length. If R is FC integrally closed domain, then each chain starting at R, finishing at S of overrings of R has length N. Now it is the sum of the height. The sum of the heights, okay? For the length involves the sum and the cardinality involves the product. Okay. Now, the exact length of chain of intermediate rings has been obtained in 1999 in a paper in Communication Algebra that says if R is an FC integrally closed domain, then each maximal chain starting at R, finishing at the quotient ring here, has length N equal the cardinality of spec R. What is the cardinality? This is spec R is the set of prime ideals. N is basically equal to the number of prime ideals of R minus 1. Number of prime ideals of R minus 1. Okay. This is the length of each maximal chain has this length here. has this length. Okay, that means other chain has length that is smaller than this one here. Now let me consider these two examples. Let me consider an integral domain whose spectrum on the left here, P1, P2 are the maximal ideals. Maximal chain here, P4 is 0 ideals. The ideal they are ordered by usual set inclusion here. A 0 ideal is included in P3, included in maximal ideals. Now the length here is the number of links to our one link, two link. Here the length here is 2, the length here is 2. Okay. Now we know in this case that the overrings they are of the form either localization of R at prime ideals, okay, of this kind, or intersection of localizations. Okay. Now for the localization, for the localization, you can see that we have 4 of them. R localized at P1, then P2, then P3, then P4. We have 4 of them. For the intersection, we have R localized at P1, intersect R localized at P2. The other localization will be one of these because of inclusion. For example, R localized at P1, intersect R localized at P3. It will be equal to R localized at P3 because of the inclusion here. So in fact, we have only 1 here. And we have 5. We have 5. Okay? We have 5. And if we use the approximation formula that said the height of m plus 1, here height is 2 plus 1, 3. Here the height is 2 plus 1, 3, 9. So here, in fact, we have 5, which is approximated by 9. There is, the approximation here is not sharp. Here in this case, we have 5 rings of the form R localized at Qi, because there are 5 ideals here. For the intersection, we have R localized at Q1 intersect R localized at Q2, because we have now inclusion between Q1 and Q2. It cannot be simplified further. And then Q1 and Q4, number 2, then Q3 and Q2, then Q3 and Q4. We have 4 of them. We have 9. Okay. And if you apply this approximation, we have 2 plus 1 times 2 plus 1, 9, exactly here. The approximation is sharp in this case. It's sharp in this case. Now, I have now one natural remark. Now, do we have, in fact, rings that integral domain that have these spectrums as these spectrum whose prime ideal ordered in this way? In fact, we can construct them easily. If we take V1 is equal Q, which is the field of rational numbers, plus X times QX localized at X, plus Y times Q of X, the field here, of Y localized at Y. This is one valuation. We can show that is the valuation domain. Another one, V2 here, we take X plus 1, Q plus X plus 1 times Q polynomial in QX localized at X plus 1 plus Y. Here, QX is the field here of Y localized at Y. Another one, similarly, we can consider V3. We can show that if we take V1 intersect V2, it is the one on the left here, And if we take V1 intersect V3, it is the one on the right. Well, in fact, we have a more general result from 1973 by Lewis here. If we start with any ordered, any rooted tree, finite here, we can always construct an integral domain whose spectrum is isomorphic to the given rooted tree. So that means we can consider any root tree, and we are sure because of this result here that we have a corresponding integral domain. Okay. Now, for second remark is about the number of, here we have found 5, here we have found 9. Why? I have defined a function here in the paper 2005, alpha function. In this way, alpha of M is equal to 1 if M is a maximal element. We start with the rooted tree. And alpha of P is the product of P prime covers P. Covers means P prime contains, it is on the top of P, and there is nothing in between in the order relation. In terms of set, P prime contains P, and there is no set in between. Okay, 1 plus alpha P prime. If P is a non-maximal element. Now let me apply the function alpha now. So apply the function alpha on the left here. This is maxima. This is why we have one here, one here. For P3, we have two coverings, P3, P1 and P2. And that means 1 plus 1 times 1 plus 1, 4. And for P4, we have one covering P4, 21 plus 4, 5. And it happens that this 5 is exactly the number of overrings here. The number of overrings here. Okay. If you apply alpha to this example here, we have here 1, and Q3 you have only 1 covering it, would be 1 plus 1 here 2. The same for Q2, Q4 here 1 here 2. And we have Q5 here, which is the 0 ideal here, it will be 1 plus 2 times 1 plus 2, 9. And it happens that 5 plus 4, 9 is exactly the number of overrings. And this is not a coincidence. We have a corresponding general result, the following here, which has been proven for principal ideal domains in 97 and for FO integrally closed domain in 2005 here in Exposizioni Matematica here. If R is in FO integrally closed domain, then the number of overrings is given by this is the number of overrings, the cardinality of the set of overrings here is equal to alpha of 0. Alpha of 0, 0 is the, here is the 0 ideal, the ideal at the bottom of the tree, the ideal at the bottom of the tree. Okay. Now, from this, we obtain easy an algorithm to obtain the number of overrings for any FO integral domain. If we start with an integrally closed domain with only finitely many overrings, if the dimension is R, now the dimension is the length, is the maximal length of chains of prime ideals. Prime ideals. Okay, then the number of overrings of R can be computed in the following D plus 1 steps. For the first step, we compute alpha of the maximal ideals. Then we go one level down, calculate alpha of P using this formula. Then we go down with this formula until at the end we arrive at 0. This is step D plus 1 because the dimension is D. Then we have alpha of 0. The product of P primes covers 0, 1 plus alpha P prime. And then alpha of 0 will be the number that we want. It is the number of overrings of R, number of overrings of R. Again, there is a corresponding results when we have an extension RS, and S is not necessarily the set of overrings, okay? But because of time, I'm only showing the result for an integral domain and its quotient field. Okay. Now, this also has been generalized, as I just said here, for normal pairs, where S is not necessarily the quotient field of R. By myself and my colleague here, and by another two people also, quite simultaneously, 2008. Now, here, this gives you here nice numerical characterizations of integral closure. If you start with R in an integral domain with a finite tree as spectrum, and alpha be the function defined as I have shown here, okay, then the following statements hold true. We have the number of overring is always larger than or equal to alpha of 0, and it is equal to alpha of 0 if and only if R is integrally closed. Okay, if you have the right number of overrings, then our ring is integrally closed. This is in Numerical Characterization of Some Integral Domains, 2011. Now, for the case where R extension of an integral domain and R star, the integral closure, usually you have this. The case R is equal to R star, this is what you have doing from the beginning. In the general case, we define a function from this interval of ring Rs to the small integral R star by Ft is equal to T intersect R star. Now, if we take a ring here, R star, for F minus 1G, it will be a normal pair. A normal pair, that means we can apply the theory that we have explained just a few minutes before. And also we have this family here of sets F minus 1G form a partition of RS. So this makes easy the computation of the set of intermediate rings. Now, if you have a flip extension of integral domains, R star, the integral closure, then the number of intermediate rings, RS, is equal to the sigma for J and this interval of ring R star and F minus 1J. In F minus 1J, it is a normal pair. We can compute the number of intermediate rings. Okay. Now, this result has been obtained in two steps. First step, when S is the quotient field, 2016, and the other step, 2020, when S is not necessarily the quotient field of R. Now, the last results does not include ring extension with zero divisors and integral extensions. We don't have, when we have integral extensions, we don't have a satisfactory theory like what we explained here. We have a compact formula that gives you the number of overrings or number of intermediate rings. We have a nice example. We take in a set with cardinality larger than or equal to 2. We take the power set of X, and we know that S here with the symmetric difference and intersection is a Boolean ring, of course commutative, with identity. The identity of the one here is X, usually denoted 1. Identity for multiplication, 0 element identity for the addition here. It is the symmetric difference denoted 0. And S is a commutative ring with characteristic 2. And R that contains the empty set is X, the smallest subrings of S with these two operations. And the unitary subrings of S are exactly the intermediate rings between R and S, because all of them, they will contain phi and X, a 0 and the 1. Okay. Now, for any element A in S, A is the root of the monic polynomial y squared minus y. Why? Because A squared here, in terms of this ring, it is A intersect A, and you know that A intersect A is equal to A. And that means A minus A, it will be equal to 0, okay? So that means here we have an integral extensions, and every element in S is a solution of the polynomial y squared minus y equal to 0, okay? And this is not a normal pair. We are not in the first case. Now, there is a nice link with this ring in the topology. Now, topology is on a set X is subset of Px that contains phi and X, and is closed under union finite intersections. We consider tau for a certain topology, consider tau complement the set of U complement, where U is in tau. We say U is the set, open set here. So U complement is X minus U, is the complement fixing U, okay? Now, We have a nice result here. If we have tau is equal to tau complement, then this is a subring. This is an intermediate rings. This is an intermediate ring. It is something in the interval of ring RS. And now, if we take X an infinite set and take I, the fin X, it is the subset of X that are finite. For I is a proper ideal of S with respect to the same operations, since X is an infinite, because I contains only finite subsets. And if we take T R plus I, A plus B, this is subring here, and it consists of the B complement B and I. As X is an infinite, so there is Y subset of X, where both Y and Y complement are infinite. Now, for every Y and Y, we have this Y is in T, but the Y, this union of Y is not in T because we will have something infinite here. So T is an intermediate ring between R and S, but T is not a topology as it is not stable by union. If we take the union, we are not in T if it is not stable by union. Okay. Now we have the theorem that is explain the finiteness conditions in this case. In the case where we have P of X, that X is finite, this is equivalent with the extension RS satisfies fifth. This is equivalent with the same extension satisfies FCP. And this is equivalent that the set of the intermediate rings is equal to the set of the topology that are equal to their complement here, equal to their complement. This is a very recent result, 2020. Now, to compute these topologies, we need partitions. We know that the number of partitions of X into K blocks is the Stirling number of the second kind here. This is the number of partitions of X into K blocks. The number of partitions, all the partitions, is the nth Bell number. It is the sum of all of these for K from 1 to n. The first Bell number are these numbers here. It happens that this Bell number is strongly related to the number of intermediate rings. We have the number of intermediate rings in this extension is equal to the Bell number of order n, Bell number of order n. Of course, n here is the cardinality of X. You can see that here the results are away from the first case of integrally closed domain. How much do I have here? Okay, now if X is in a partition of if union from A1 to K, Xi is a partition of X into K blocks, then the corresponding subring Px consists of X phi and all subsets X resulting from a union of some of the Xi's. Okay, so you can say the ring generated is Xi. For example, if X is equal to 1, 2, 3, then if you take this partition, then T is equal to the whole of Px. If you take this partition here, then T is equal to only this part of Px, etc. This explains the correspondence between partition and the intermediate rings. Now, another result here, if X is a finite of cardinality and larger than or equal to 2, then the length here is equal to n minus 1. The length here is equal to n minus 1. And this is the last result in my talk. Thank you very much for your attention.